Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing today? It's our last week together. Oh, let me see some questions. So, part two. Yes. Yeah. So, Stephen, answering your question. So, basically, each part of the code, part one, part two, part three, I formatted Figure 6 to give you, what the solution should look like. And so if you did everything correctly in those parts, then figure 6 should show, your figure 5 should match your figure 6. So figure 6 is it's different for each of the different parts because for each part you implement something different. And so when you do each of the parts, you can check your solution against figure 6. Yeah. Mm-hmm. Okay. So the plan for today, actually, the plan for today is just to have you guys work on the project, and I'm going to be available here for the entire lecture to answer your questions. So I know a lot of you guys have been working on the project since last week, so I've been answering your questions individually. But usually when I do kind of a big project like this that involves a lot of coding or use of computer software, normally in person we would be doing this in a computer room. So you guys would be working on this, and this is what I usually like to do is I usually like to go around and kind of help people individually. So today I kind of want to simulate that a little bit, and so it's going to be a little bit difficult just because of the just because we're on Zoom. But if there's any questions or anything that you guys are stuck with your code, if you want me to look at your code, I'm happy to do so. And if you want us speak privately, we can go into a breakout room too. But today is just kind of working on the project and just having me available here just to answer any questions. So, beyond that, I didn't have anything else planned for today. So if you feel like you're progressing well on the project, and you don't need any feedback, you can sign off for today. But the plan was just to kind of help people along with their projects. I know it's a lot of coding, and I know not everyone has a lot of background with coding. So I want to make sure that everyone's kind of on the same page and with everything. So and so if you have a question, you can message me in the chat in the room, or you can message me on Discord. If you're okay with me answering your question for the whole class, I can do that. But if not, we can meet inside like an individual breakout room, and we can talk there too. Okay. So the floor is open. So anything that people want to ask, you guys can go ahead. All right, question in the chat. So question, figure 5 should match what shows in figure 6 at each part of the project. That's correct. Yes. Yeah, so for each part of the project, figure 5 and figure 6 should match pretty well if you did that part correctly. Oh, with that said, there was a small typo in my implementation for part 3, at least for the reference solution. So if you're on part 3 and you're not getting it to match, I would download the updated part 3 starter code from Canvas, because there was a small typo in the reference solution, but I've corrected that, and so the new part 3 should match up pretty well. Yeah.
Is the image that you have on the screen right now, is that the answer?
This is part 1, so this is the answer for part 1 right now.
Okay.
Yeah. Yeah. So
In our
oh, go ahead.
oh, in our figure 5 is supposed to match this, right?
Exactly. Yes. Yeah. You might get a small discrepancy in the corner right here. So in the corner, you might have 75 degrees, but on the reference solution, I have 100. But that's mostly just a function of how the Dirichlet boundary conditions are implemented. But don't worry about that too much. So the corner nodes are usually a little bit, some weird things can happen in the corners, but besides this one, everything else should match up pretty well. So I would say you might get some mismatches here at this corner, maybe at this corner, and maybe at this corner. So basically, whenever you have two edges meet and they have different Dirichlet boundary conditions, you might get a different solution depending on the order in which you did your operations. But you can kind of ignore the corner. So everything else should look pretty close to each other. Yeah, definitely I can do that. Okay, let's take a look. Let me stop sharing and then I'll take a look at your code. Okay. Yeah, so I think this is good to kind of go over as a class. I have gotten several questions on this, which is how to implement the Dirichlet boundary conditions. So let's actually go over that together as a group. Okay, and so this is going to be code that you're going to need for part 1 of the code, which is how to implement the Dirichlet boundary conditions. Okay. Okay, and so I think the confusing thing about this part of the code. Actually, let me clear everything here. Okay. And so the Dirichlet boundary condition, the way that we're going to apply it is we're going to run through our similar process that we've done before, where we go to the row that we need to in order to that corresponds to the place where we're going to apply a Dirichlet boundary condition. We're going to zero out the entire row, and we're going to put a 1 on the diagonal, and then put the Dirichlet value on the right hand side. Okay, and so the loop that I've given you for the starter code looks like this. Right? And so what I'm doing here for the loop is that you can see that I'm looping over every edge in the in our Dirichlet edges vector. Okay, and so just to kind of remind you guys, this Dirichlet edges was defined up here. Okay, right. And so what this part of the code does is that it defines which edges that we want to apply our Dirichlet boundary condition. Okay, and so let me kind of illustrate that with the figure here. Okay. All right, so let me go ahead and evaluate this parts of the code. Okay. All right, so let's go. So let's look at this figure right here. Okay. So figure 2. And so figure 2, you can see we have our domain, and each of the edges here are labeled with a different number, right? So this edge right here is given with index or a label 1. This it's kind of hard to see, but this edge up here is given with the index 2. This one's number 3, 4, 5, 6, 7, 8, and we have a couple interior edges, 9 and 8 and 9, and we have 10 right here. Okay, and so the way that we're going to apply this Dirichlet boundary conditions is it kind of goes back to how we did boundary conditions for our frame code, right? And so for our frame code, if you remember the syntax that we used for that was we defined the basically the degrees of freedom that we want to apply boundary conditions on, and then we specified the boundary conditions here. So I guess this part's new because since we're doing a heat equation, we actually have to supply the actual temperature there. Okay, and so you can see here the list that we have lists all of the exterior edges. Okay, and so we have 1 and 3, and so edge 1 is right here, edge 3 is right here. Then we go 4, 5, and then 6, and then 2, and then 10, and then 7. So basically, I'm making just a loop all the way around the domain. Okay, and so I'm leaving out 8 and 9 because those are interior edges, and those we don't want to apply any boundary conditions on. So we're going to ignore edges 8 and 9. Okay, but we're going to do every other one. And then what we have on down here, these are the values that we want to specify for the Dirichlet boundary conditions for those edges. Okay. And so we want to apply a temperature of 100 on edge 1. We want to apply a temperature of 75 on edge 3, 75 on edge 4, 75 on edge 5, 75 on edge 6. And then on edge 2, we want to specify a temperature of 50. On edge 10, we want to specify a temperature of 50. And then edge 7, we want to specify a temperature of 100. Okay. And so the first thing that we need to do is we need to loop over all of these edges. Okay. And that's what we're doing here. Okay. And so this loop, what it's going to do is that on the first iteration of the loop, we're on this edge right here. Okay, so that's what this loop does. So it's going to repeat 1, 2, 3, 4, 5, 6, 7, 8, and so it's going to repeat 8 different times. Okay, with each time the loop iterates, we're going to visit a different edge. Okay. Okay. And so the first thing that I give you in the starter code is this special function right here. And so this is a function that you're going to need to specify the boundary conditions, but otherwise it's you wouldn't be able to know what it is unless you're familiar with this package. And so what this function does is that I'm calling this function here called find nodes, and what it does is it's going to return all of the nodes that are on this boundary. Okay. And so let's take edge 1 for instance. Okay. Actually, let me make this a little bit bigger. Actually, 0.2 is fine. Okay. And so edge 1, remember, is going to be this entire edge on the left-hand side right here. Okay. So let me blow this guy up a little bit more. Okay. Oh, wrong one. You want this one. Okay. Okay. And so if we look at all the nodes on this side, this edge nodes here, this edge nodes is going to return a list of all of these different numbers here. Okay. And so the first time for edge 1 right here is going to return a list that contains the entries 1, 29, 30, 31, 32, and 2. Okay. Okay, so the important thing to note is that this edge nodes here is a vector, and so we need to loop over this this edge nodes vector here. Okay. Okay. Because remember what we talked about last time is that these nodal index numbers here, we're going to use those. We're going to use those to refer to the same rows in the global stiffness matrix. Okay. Okay, so let's write a loop to visit every node in the edge nodes vector. Okay. So let's do 4. We'll call this IN. So you can call it whatever you want, but I call it IN to just denote that this is a loop over the nodes. Okay. And so this is going to be 1 to the length of edge nodes. End. Okay. And then the nodal ID, this is going to be here we're going to reference the edge nodes vector. So this is going to be edge nodes at IN. All right, so now that we know the nodal ID for each of the nodes here, or at least we're obtaining it, now we can use this to modify the global stiffness system. Okay, and so first let's zero out the entire row. Okay, and so let's see. So we're doing this in global, right? Yes. Okay. So first step is to always with our Dirichlet boundary conditions is zero out the entire row. Okay. And so we're going to do k global. Right. The row that we're going to enclave global is going to be referring to that nodal ID. Okay. And then we're going to zero out all the columns. So we're going to need a colon right there. Okay. Right. And then we're going to set this equal to a zeros vector. Right. Let's see. Right. And that zeros vector is going to have one row, and then the number of columns in that vector is going to be the number of nodes in the mesh. Okay, because that's going to be, remember, that's the size of our global stiffness matrix, right? So if we go back up here, our global stiffness matrix is n nodes by n nodes, right? And so in order to make the entire row zeros, we have to set it equal to a zeros vector. Okay. All right. Next, after we zero out the entire row, we need to set the diagonal entry equal to 1. And so we're going to do that with k global at nodal ID is equal to 1. Okay. Right. And so this will basically set the diagonal entry equal to 1. Right. And then the last part, which I'll leave to you guys, is you need to set the appropriate value for the right-hand side forcing vector. And so this is going to be F global. And so you need to do something for F global. Okay? And so I'll leave that up to you guys. Okay. But basically, this is kind of the syntax that you need to use for this part of the code, where you loop over all of the different edge nodes, and then you obtain their nodal ID. Okay. And then you set the appropriate rows and and the global stiffness matrix equals 0. You set the diagonal entry equal to 1, and then you set the appropriate value on the right-hand side vector. Okay. And so I'll give you a hint. So in order to do this part right here, you need to obtain the Dirichlet values. Okay. And so you're going to need to use Dirichlet values at some point in this code here too. Okay. All right, so hopefully that gives you guys a little help with that part, because that's just like kind of we talked about last time when you're using the connectivity matrix, using this edge nodes matrix here is a little bit confusing if you're not sure what's inside that vector. But hopefully with this, that gives you a little hints on how to do that Dirichlet boundary condition. Okay? And so it's the same thing that we've always done. It's just the formatting and the syntax I think is a little bit different because it's an unstructured mesh. Right. Does that help you out with that part? I kind of quickly looked at your code. I think that was kind of the main thing, but at least that was the thing that stood out when I looked at your solution field. Okay, great. Okay. Does anyone else want me to look at their code to help them troubleshoot anything? Eric, to answer your question, usually I like to put parameters into the zeros function just to make sure I'm creating a zeros vector that has the proper lengths. But I think MATLAB should be smart enough that if you just leave it blank, it should be okay. But I think it's just kind of force a habit on my part to kind of do that, because it's but I think MATLAB's kind of gotten smarter over the years. Steven.
Professor?
Yep.
Can I ask a quick question?
Yeah, sure.
I'm confused on the K global. So is it supposed to be the size of the K global is supposed to be n elements by n elements?
It should be n nodes by n nodes.
N nodes, okay. By n nodes, okay.
Yeah. So actually, that was a good question I got from someone over the weekend too. Because this mesh has a lot more elements than nodes. What you should see is that the your K global will probably be smaller than the number of elements that you have, and that's totally normal. And so if you look at this mesh right here, because in 2D and 3D, the effect is even more pronounced, but you can see in this mesh right here, let's look at this node right here, 65. And so node 65 here is connected to 1, 2, 3, 4, 5, 6, 7 elements. And so that's pretty common that, a node will border at least 3 elements. And so because of that, you end up with a lot more elements than you do nodes. And so, don't panic if you have, your K global is smaller than, smaller than the number of elements that you have. That's by design.
Okay.
I have been looking for the empty thing. Okay, I was looking for it. I wanted to see if I would be able to pull the blinds open. Oh my god. With this. I was trying to do it with the candy canes, but I didn't have enough grip. So I tried doing it with the duster. It was too bendy.
Professor.
Yep.
When calculating the element stiffness matrix, we don't really care about the shape functions, right? Since this is a triangle, and when we get the derivatives, it's only like 1, 0s, and something.
Yep. No, you're absolutely right. So that was kind of the typo that I mentioned in class last time, because I think in the starter code I left a hint there to compute the Gauss locations, but you don't actually need that for the element stiffness matrix, because when you compute the derivatives, they're just constant values, and so you just have to perform multiplication with that. Yeah.
Okay, and when we're calculating the Neumann boundary condition, then the Gauss points are going to change, right, to the ones that you put in the file.
Yes. Yeah. So so when you're evaluating the Neumann boundary conditions, remember you're doing a 1D integral now, so it's no longer a 2D integral, and so the locations of the Gauss points are going to change. Yeah.
Got it. Thank you.
Oh, one other thing that I forgot to mention for the Neumann boundary conditions, that I forgot to mention in the project specs, is that normally when we're doing the a 1D Gauss quadrature, we multiply by the length of the side divided by 2, right? That was kind of like our Jacobian factor. So actually, let me go ahead and share my screen again. Let me pull up those notes.
What Scooby-Doo while I was simulating my stuff?
Let's see. I think it was this one.
I was watching Vampire Diaries this morning. Again? With her. Oh, okay. She's pretty, because she didn't leave until like, she comes to work like 1:30. She works kind of close.
Ariana, I think your mic is on.
She's on the season where they get stuck in the health stone, and like the episode we left off.
Okay. So normally, so remember when we did our 1D Gauss quadrature, we had to multiply by this factor right here, dx dxi, right? And so when we computed that, that ended up being, the length of the side, which was x2 minus x1 divided by 2. But remember, that was only for the case when our integration bounds were -1 to 1. And so for the project, we have a little bit more of a unique case. Instead of integrating from -1 to 1, we're integrating from 0 to 1. And so instead of this Jacobian factor being the length divided by 2, the only thing that you need for that is just the length. And so I think in the starter code for part 3, what I had you do was compute the distances. Compute the edge lengths, right? And so later on, when you add the contributions to the element stiffness matrix, you would just need to multiply by distance, not distance divided by 2. So that's another thing to keep in mind once you get to part 3 of the project. Yeah, that was kind of the small typo I had to correct in the solutions today. Yeah. All right, so the matrix that contains the shape function derivatives. Oh, sure. Yeah, so when you're, so let me repeat first, and then I'm gonna look at Stephen's question, and then Argan, I'll answer your question. And so what I basically just said was that when you're doing the Neumann boundary conditions for part 3, you know, normally when you apply that 1D integral, you know, you have to multiply by the length of the edge divided by 2. I think that's what's said in the in lecture notes 12 actually. Because we're doing an integral on a triangle where the bounds are just from 0 to 1 and not -1 to 1, then what you're going to multiply instead is just the length of the element, not length divided by 2. Yeah. So actually, you know, let's actually go to lecture notes 12, and I think that's probably a good place to illustrate that. And so in lecture notes 12, I'm looking on page 11, you know, this is where we computed the Neumann boundary condition on top of the element, okay? And so you can see right here, I have this factor right here for the length of the element divided by 2, okay? But that was for the case for the rectangle. So in the rectangle, we're integrating from -1 to 1, okay? But for the triangle, we're only integrating from 0 to 1. And so because of that, you know, we don't have this divided by 2 factor here. So we just multiply, we only going to multiply just by the length of the element, or the length of the edge, okay? And so there should be no divided by 2 when you're doing part 3 of the project. Mm-hmm. Yep. All right. All right, Stephen, so I'm looking at your F element matrix. It's a little bit hard to tell because, you know, the mesh is always going to be a little bit different each time that you produce it, so it's hard to know. But just by looking at this this matrix here for this is part 2, correct? And so if it's part 2, then, you know, the entries for F element should all be relatively close to each other because the elements are kind of in the same spot, you know, but the entries will be slightly different from each other just because you're evaluating it at different Gauss points. So this looks pretty good to me. Although it's hard to really know without, you know, going deep into the code, but that F element does look good to me. Yeah. All right. So
okay,
Argan,
thank you.
Yeah. Yeah, so Argan, your question is, what would I call the matrix that contains the shape function derivatives? And so I usually call that B sub G, if that's the physical derivatives. But if not, I just call it the dn matrix. Yeah. Yeah. Mm-hmm.
Sir?
Oh, hello?
Yeah, sorry. Yeah, I'm just gonna say it. So for the part 2, so for the F global vector, we have the original Dirichlet values, and on top of that, we're supposed to add those F element from the Gauss point contribution to that.
Yes.
Vector, right?
Yes. Yeah. Mm-hmm. All right, so question in the chat is, can I please go over how to loop over the Gauss points for all 3 nodes in an element part 1? Yeah, I can definitely do that. All right, so let's share screen again. Okay. Okay. And so that's, you're referring to this part of the code right here. So this is part 1, and we're looping over all the Gauss points, okay? All right. And so I think the part that's a little bit confusing for everyone is how do we add the contributions to each of the different from each of the different Gauss points, right? And so when we look at the code here, we can see that we have this summation, right? So we're going to do B sub G transpose times K times B sub G times the determinant of the Jacobian times the Gauss weight, okay? Okay, so let's go ahead and go ahead and start implementing that in the code. Right? Okay, and so the first thing we need to do is we need to compute the shape function derivatives at the Gauss points. And so, you know, that's kind of what everyone was kind of mentioning with the ones and minus ones and zeros. So, you know, that part is okay. Next, you have to compute the Jacobian matrix. And so you're going to combine this vector right here for the positions, which have the x coordinates and the y coordinates for each of the different nodes, and you're going to multiply it by the what you got in the previous part. Okay? And then from there, you're going to multiply. You're going to compute the inverse of the Jacobian and the determinant. Okay, and so you know those are fairly simple to compute. And then from there, this is the line that gives you BG, right? So BG is basically going to be equal to the inverse Jacobian multiplied by the shape function derivatives in the parametric space. So this is dn parametric. Okay. Okay. And so now that we have this information, we can go ahead and sum them up for the element stiffness matrix. Okay. And so the easy way to kind of do the summation is I like to use this syntax here. Okay. And so we're going to use basically the update syntax that we've used kind of in the past. Okay. And so what this basically says is that the element stiffness matrix for this element, okay. And so remember, I'm using this colon notation to basically tell me to, or I'm telling MATLAB to grab all the rows and all the columns in that in those directions. Okay. So remember, KLM here is a 3 by 3 by n elements, and so by using this colon notation, I'm returning a 3 by 3 matrix. Okay. And so what I'm saying here is that you know the new entry for K element is going to be whatever's there before. And then to that, I'm going to add the new contribution from this Gauss point, okay? And so this is going to be B G transpose, okay, multiplied by K, which is going to be our thermal conductivity, times BG, okay? And then we're going to multiply by the Jacobian determinant, okay? And then we need to multiply by the weight for this Gauss point, okay? And so the weight, you know, for a 3-point Gauss rule is going to be 1/3. Okay. Okay. And so to put this in code, we can basically say that this weight is going to be 1/3. Okay. And then this BG transpose and BG, you know, you obtain that from the previous parts of the code. Okay. But if you set it up like this, basically it's automatically going to add up all the contributions from the 3 points, because you're basically going to repeat this 3 different times. And then, but each time that you repeat this BG transpose and this BG and this Jacobian, they're going to be different because you're evaluating it at the different Gauss points. In theory, they would be, but in this case, they're actually all exactly the same because the derivatives of the shape functions are just constants in this case. But yeah, if you do this format with this for loop, then you can do it basically does the summation for you. Okay. So someone actually brought up a good point today in office hours that you can actually do this loop here for the element stiffness matrix in a different way. Okay. And so if you kind of remember from a previous lecture, we went over kind of an explicit way to do the triangle for you know, based off its area. Right. Oh yeah, no problem. And so if you want to use this method instead of the Gauss quadrature, that's totally fine with me too. And so I think that was in lecture notes 11. Okay. And so if we go down, right, so if you follow the example basically here on page 9 of lecture notes 11, you can see that I computed the element stiffness matrix used based off of the coordinates and based off the area. Okay, and so with this loop, I always fill up the wrong one. And so with this loop right here, we can obtain x1, x2, and x3, just fine using kind of what we did before. And then from there, you can directly compute the shape function derivatives according to this, and then you just simply multiply them together. Okay. And so if you want to use this method here, this actually works perfectly fine. So that's if you don't want to use Gauss quadrature for the element stiffness matrix, this works perfectly fine. The only thing I would be careful of is that if you're going to use this method, that the area that you compute, make sure you take the absolute value, because if you get a negative area, that's going to mess up all your calculations. So sometimes when you plug in the coordinates directly here, you're going to end up with a negative number. And if you do that, just make sure to take the absolute value. But everything else you can kind of follow to a T. And I think it probably would result in a code that's maybe roughly the same length as the Gauss quadrature, but you'd have one less loop to worry about because you don't have to loop over the Gauss coordinate. So if this makes more sense to you, and then you can go ahead and use this, and you should get basically the exact same answer. Yep. So the area basically comes from the integral. Yeah. So if you're struggling with the Gauss quadrature for part 1, this is another option for you. But you're going to need but for part 2, you basically have to use Gauss quadrature for that one. And so if you can get the one for part 1, then part 2 is a little bit less of the step up. But this is an option for you if you just want to do part 1. Right, so the question in the chat is, can I explain the Neumann edges and values? Yeah, definitely. Let me go pull that up, okay. Okay, I think this is the figure that I want, okay. Okay. All right, so so part 3 of the code is going to have you guys do the Neumann boundary conditions. So basically, the way that you need to do that is you need to perform a 1D integral over this over an edge of this element. Okay, but as I was explaining in the specs, the tricky part here is determining which edge of the triangle is actually going to be the one that you need to do the integral over. Okay. Because each of these edges here, if we kind of look at element 96 right here, 2 of these edges are on the interior, so we don't want to integrate over those ones. The only one that we want to integrate over is basically the one that I've highlighted here, which is on the edge. Okay, and so the tricky part with doing part 3 is determining which edge exactly that we're going to that we need to use. Okay, so that's kind of what this this whole kind of song and dance here for part 3 is. So part 3, the only thing you need to implement is just this loop right here, but it's tricky. Okay, so the first thing you need to do is we need to even determine if there's an edge on this boundary. Okay, and so if we kind of go back to the project specs, what can happen sometimes is that if we're finding all the elements that border this edge, we might get something like element 98 right here. Okay, and so element 98, it only has one node that's on the edge. Okay, and so when it only has one node, then we actually can't apply the Neumann boundary condition for this element because it doesn't have an edge that's on that boundary. Okay, and so this first part of the code right here is basically determining how many boundary nodes that we have. Okay, and so what you need to do is you need to use this MATLAB function called isMember to basically determine if the node is on that edge. Okay. And so to do that, first thing you need to do is you need to get the nodal IDs for each of the 3 nodes in this element. Okay. Okay. And so for this, what I mean by this is you need to get N1, N2, and N3. Okay. And so hopefully, you've used this in a previous part of the code. We actually went over this last week too. Okay. And so the way that you determine if this node is on the boundary, you're going to use this function called isMember. Okay. And so the syntax for that is going to be isMember. I'll fill out the first one for you guys. Okay. And so first thing we need to determine is if N1 is on the boundary. So we're going to do is member N1. And then we're basically going to see if N1 is a member of this vector right here called Neu nodes. Okay? And so this Neu nodes right here, you know, I've defined this to be basically all the nodes that are on that boundary edge. Okay? And so this will basically return a list of all the nodal IDs that are on that edge. Okay? And so by checking if the N1 is a member of Neu nodes, we can see if that's on there. So if it is, then we kind of mark it. So this is kind of a way that we can have like a checklist in you know, in code. Okay, and then we have to do that for each of the different nodes too. So we have to do another expression for N2 and another expression for N3. Okay. Okay. And so from there, you know, we need to check to see if we have two nodes on the boundary. Because if we have two nodes on the boundary, then we know that, you know, there has to be an entire edge that sits on that boundary. Okay. And so the way that we're going to check that is to say that, you know, if we sum up this boundary nodes, and if the sum is 2, then, you know, we have an entire edge that's on that boundary. Okay. And if not, you know, if the sum is only 1, then we have a case where, you know, like element 98 right here, where we only have one node on that boundary. Okay. And so if we only have one node, then if we only have one node from the element that's on the boundary, then we can ignore it and we can kind of just move on. But if we have two nodes, like element 96 right here and element 120, and so for both of these guys, you know, we have this node and we have this node on the boundary, then we can kind of move on and start to apply the Neumann boundary condition. Okay. Okay. All right. And so now we get into kind of the next tricky part is to tricky part is to determine which edge or which edge on our triangle is actually on the boundary, right? Because for the triangle here, you know, we have 3 different edges. Okay. So remember, this is the triangle in the isoparametric domain. So this is after we've done our mapping. Okay. And so when we map, say, let's say we want to map this element 120 here, and we map that into the parametric domain, it's not clear, you know, where this edge right here went, right? And so when we perform our mapping, you know, this edge went somewhere in our triangle here, but we don't know which edge that is, right? So it could be that edge could have been mapped to edge 1, 2. It could have been mapped to edge 2, 3, or it could have been mapped to edge 1, 3 down here. Okay, and so we don't know, and so actually there's no way to know, you know, without performing some more tests. Okay, and the test that we're going to perform is we need to check which of the elements of this boundary node were equal to 1. Okay. And so, you know, if boundary nodes 1 and boundary nodes 2 were equal to 1, and so what that tells us is that nodes 1 in our isoparametric triangle and node 2 in our isoparametric triangle, both of those guys are sitting on the boundary, and so our boundary edge is going to be the edge that's in between them, so edge 1, 2. Okay. All right. And so if our edge 1, 2 is our boundary edge, the first thing we need to do is compute the length of that edge. Okay. And so we need to basically obtain the x coordinate and y coordinate for nodes 1 and 2. Okay. And so to do that, you need to use the nodes vector. Okay. So we went over this last time on how to use that to obtain basically x1, x2, x3, and y1, y2, and y3. Okay. And so since you know that you're using x1 and x2, so let's say that we know x1, x2, x3, and then y1, y2, y3. Okay. And so since we know that we're using nodes 1 and 2, the distance is going to be square root. And so I'm just going to use the distance formula here. So this is going to be x1 minus x2 squared plus y1 minus y2 squared. Okay. And then after that, we need to set the Gauss points. Okay. And so the Gauss points, I gave it to you in the code in the specs right here. And so if you're on edge 1, 2 right here, you know, you need to set the Gauss points equal to these guys. So we need to have 2 of them because we're doing a 2-point Gauss rule. Okay. And so I'll let you guys basically code this up. And so what these basically correspond to are, the locations that I have boxed in green right here. Okay? And so for edge 1, 2, you can see that we have a coordinate at √3 - 1 over 2 over √3, comma, √3 + 1 over 2 over √3. And so that corresponds to this box right here. So that's the xi and eta coordinates for this box. And then this one right here, this other coordinate corresponds to this, the location for this box right here, okay? So I think it's a little bit easier to tell on the horizontal one. So let's look at edge 2, 3, okay? And so we basically want the xi and eta coordinates for this box and the xi and eta coordinates for this box right here, okay? And those are given by this one right here. So the first one is gonna be 0, comma, √3 - 1 over 2 over √3. And so that's gonna be the coordinates for this box right here. And then the other one, which is +1, is gonna be the coordinates for this box, okay? And so I gave you the Gauss coordinates for these because they're a little bit weird because they're we're integrating from 0 to 1. Okay. Okay. And so once you have the Gauss points, then you can compute the values of the shape functions at these Gauss points. Okay. And so basically what you're going to have is you're going to have each of the 3 shape functions. You're going to have n1, n2, and n3. Okay. And these are going to be evaluated at GP1. And you're also going to have the shape functions evaluated at GP2. Okay. And so that's, you're going to use the formulas for the shape functions and the Gauss points that you just computed in order to do that. Okay. And then from there, you can basically put these 2 guys into vectors. Okay. Okay. And so you can have a n-GP1 vector. Okay. And so this can be like n1 GP1 semicolon n2 GP1 semicolon n3 GP1. Okay. And so basically I just took our 3 shape functions and I just stacked them on top of each other into a vector. Okay. And then from there you can just add their contributions to the element stiffness or the element forcing vector. Okay. Right. And so for that you're basically doing, where is it? You're basically doing this part of the code right here. Okay. Right, so you have your shape functions evaluated at the Gauss points multiplied by the Neumann value, and so the Neumann value is given to you in the code, and so I think that's given by the value of flux. Okay, and then you have your length parameter, but remember instead of length over 2, we're just multiplying by the length. Okay, and then you have your weights. Okay. But since we're doing a two-point Gauss rule for a 1D integral, your weights in this case are just going to be 1 each. Okay. All right. So does that make a bit more sense for the Neumann boundary condition?
Professor, the shape functions are going to be the same.
So they have the same functional expression. So n1 is still going to be xi. N2 is going to be eta, N3 is going to be 1 minus xi minus eta. But when you evaluate them at the different Gauss points, they're going to end up with different values.
Yeah, of course. Okay, thank you.
Yep. Mm-hmm. All right. Any other questions on the code? I'll stick around. I'll keep sticking around until 6:45. So if you guys got questions, don't feel like you have to cram them in now. But just want to let people know the floor is open.
Professor,
Yep.
can I send you my starter code? I'm just getting an error on the global stiffness matrix. I was wondering if you can maybe go over it.
Yeah. I can take a look. Go ahead and send it over.
Thank you.
Yep. Yep. So Hassan, so your question is in part one, because the shape function derivatives are constant values, we don't actually need the Gauss point locations. That's right. Yeah. So yeah, that was kind of a mistype on my part, and I left a comment in the starter code to say that you need the Gauss point locations. But since the shape function derivatives are just either 1, -1, or 0, then you don't need that. So and so for that part of the code, then you can just leave that off. All right, so Alex, your question is, in MATLAB, if you use the same variable twice, do you need to redefine it, or can you use it again? So so you can use it again if you define it to have a different value, that's totally fine. But just be aware that if you define if you use the same variable name and you give it a different value, kind of the first value that you gave it was basically lost. But if you don't need that value anymore, then it's totally fine to reuse variable names. Yeah. And so I think the only actually MATLAB it might be okay, but usually when you define a new variable inside a loop, usually you can't use that same variable outside the loop. So let's say that I wrote a for loop, and inside the for loop I made a variable like x_g. If I try to access that variable basically outside the loop, normally it doesn't. You shouldn't be able to do that. But I think in MATLAB it's okay because I think they maintain kind of the same workspace all throughout. Yeah. All right, so Naveed, I got your starter code. Let me go ahead and take a look. Okay. Yeah, so right now you're getting an index out of bounds exception. So the what that means is that you're trying to access an entry in the matrix that doesn't exist. And so it's happening on line 112. And so on line 112, you have basically 3 matrices that you're trying to access. So you're doing K global once, K global again, and then KLM. And so the error is going to be in KLM because you're trying to access it at N1, N1. But remember, KLM is just a 3x3 matrix. And
so
so
it's a 3x3.
Yeah, KLM is a 3x3, but K global is so you're going to use N1 for N1, N2, N3 for K global, but since KLM is just a 3x3, you need to take that into account when you're accessing it.
Okay, so should it just be all IEs for a K element?
It shouldn't be IE, so your IE is in the right slot for that one actually, but you need to change the N1s to something else because it's only a 3x3.
Okay.
Yeah.
All right. Thank you, Professor Tran.
Yep.
Professor.
Yep. Mhm.
Actually, I already sent my part 1 and part 2. I want just you check it, them, and is it okay? I gonna go to part 3.
Okay.
Thank
I mean,
you.
do the solutions match the
The first solution, yes, the match, but the second part, I didn't know how is the solutions.
Okay, let me check your part 1. Looks like your part 1 needs a little bit of work too. So I'll point you at least in the right direction. Yeah, so I think there's still an issue with the Dirichlet boundary conditions, kind of like what we were talking about in office hours today. And
Maybe
so,
that is, yeah, I think the F global must be, I have to work
yes,
on it.
yes,
Yeah.
So so I would focus your attention on that. But I think everything else looks. Let me kind of check everything else. I think everything else looks good. But yeah, that's definitely an issue. Yeah, that needs to be addressed. Right. And then your part 2. And so the only thing that's different in part 2 is the forcing vector and loop. So let me look over that. I think your forcing vector and loop looks good. Let me just double check real quick.
Thank you.
All right. Oh, so you are missing the weight. And so remember when we're evaluating the Gauss quadrature for a triangle, you know, the weight is 1/3. So you do need to.
Oh, yeah. Actually, yes, you're right.
But besides that, I think it looks good. But yeah, I think go ahead and fix the Dirichlet boundary conditions, and I think that should put you in the right direction.
Okay, thank you, Professor.
Yep. Okay. Yeah, Stephen, I can take a look. Okay. Let's see. Oh, Stephen, you need to copy and paste your code for the element stiffness matrix from part 1. And so that on line 60, where I say insert your element stiffness code from part 1, You need to copy and paste basically what you did for the element stiffness matrix and put it in there. So I think that's the main thing that's missing. I'm actually surprised that your code actually ran without the element stiffness matrix, because your forcing vector code looks right to me. Oh, you did copy and paste it. Okay, oh, never mind. It's just you had the header twice. Okay. All right. Okay. One thing I do see for your element stiffness matrix is that you're kind of summing up the element stiffness matrix 3 different times. Oh, but it doesn't matter because you're kind of rewriting it. Okay. Okay. It should be okay. Right. Let me do this. Let me compare with my code. Let's see. Let me answer Argon's question really quick because I think he's just getting a quick error. Oh, Argon, I think it looks like thermal model does not have a mesh. Okay, line 213. So I think you have to when you uncomment the end of the code when you're checking the reference solution, you have to uncomment all of it. I think it's missing some of that its code. So I think it's probably missing the line thermal model equals to something. Yeah. Oh, let me see. I would double check with this. If you download a fresh starter code from Canvas, then just double check that you have basically all the everything for the reference solution, because the code for the reference solution should be self-contained, where it doesn't depend on anything else in the code. So I would just double check that you didn't accidentally delete something or something like that. Oh, okay. Okay, good. Hmm? All right, let me go back to the solution. All right, Steven, I'm still checking your code right now. Negative values. You might get some negative values just from the forcing function, but I think I wouldn't expect there to be, because the forcing function is positive, and the shape functions themselves don't go negative. So that might be something. Negatives in the element stiffness matrix is okay, because they're that's okay. But the forcing vector, I don't think should be negative.
Professor Tran,
Yep.
can I ask you one quick question?
Yep.
For the Dirichlet boundary conditions,
Mhm.
what does it mean by length Dirichlet edges?
Length Dirichlet. So the Dirichlet edges is a vector, and so that contains all of the edges that we want to apply Dirichlet boundary conditions are. Length is a MATLAB special function that just returns the length of that vector, and so however many entries are in there, that's what length returns.
Okay.
Mhm.
All right. Thank you.
Mhm. Let's see, generation 1 and 0. Yeah, you should leave generation as 1, but that's just for debugging. So so that's optional, actually. Yeah, so you don't need that one. Hang on. Inder, I see your question, but let me take another look at Stephen's code just really quick. Oh, okay. Stephen, so I think I see one thing that could be the issue. So I see that between lines 272 and 281, that's where you're adding the contributions from the element forcing vectors to the global forcing vectors. But this needs to happen before you apply the Dirichlet boundary conditions. So remember the Dirichlet boundary conditions, that's always the last thing that we do before we solve. Because remember, when we're applying the Dirichlet boundary conditions, we're modifying, we're overwriting, entries in the, stiffness matrix and in the global forcing vector. And so you basically need to, you need to settle all those things before you apply the Dirichlet boundary conditions. So I think if you move that part of the code up, I think that should help your code. Yeah.
Okay, let me try it. Thanks.
Mm-hmm. Okay, so Inder, your question is, how do we compare, or where do you compare the figure to see if you're getting the right figures for each part? And so each part of the code I've formatted so that, figure 6 that shows up, that should be the solution that you get from that part of the code. And so if you compare your solution in figure 5, so figure 5 is what your code is producing. If you compare the solution in figure 5 to figure 6, those two things should match. And if not, then you need to debug your code a bit more. Yeah.
Professor?
Yep. Mm-hmm.
So I moved that for loop right above that Dirichlet application.
Yeah.
And the plot looks pretty similar, but I'm still missing that little yellow, dark yellow area and the dark blue area on the bottom right square.
Okay. Can you send me a screenshot to see what the plot looks like?
Sure.
Let's see. Okay. Yeah, it's closer, but yeah, not quite. Okay. Go ahead and send me your updated version of the code, and I'll take a look. But I do need to take off because it's 6:45. But I'll take a look at it. If not tonight, then tomorrow morning, and I'll take a look and I'll get back to you. Okay. Okay. So that's all we got time for today. So if you have more questions with the code, definitely send me your emails. I can look at your code too. If you're having specific troubles with an errors or something like that, or you can't get the plots to work out, you can shoot me an email. But on Wednesday, the plan is I'm going to actually give a little bit of presentation on my own research. Just because for my own research, I use a lot of these finite element stuff. So I wanted to give you guys kind of a sense of some other applications for this that you might that we haven't had a chance to really see in this class yet. Okay, so that's the plan for Wednesday. But for the rest of this week, office hours or not, if you're having trouble with the project, definitely shoot me an email, because I know it's a tough project with a lot of coding. All right, so have a good night, everybody. Thank you guys for showing up, and I'll see you on Wednesday.
Thank you, Professor.
Thanks, guys.
Thank you.
Yep.